Okay, let's do this. Hello, can everybody hear me? Am I audible? Am I visible this time? Excellent. Welcome to another Meyersound webinar. This time we're going to talk about an introduction to Mapp XT. But before doing so, as always, I will instruct you a little bit about the Zoom platform that we're about to use. So without further ado, let me share my screen and let's get this thing going. Okay, there we go. Okay, introduction to Mapp XT. But like I said, before we start doing, let's look at Zoom briefly. So we're using the Zoom, a video communication platform, which means that you are having a window in front of you, not unlike the one you see on your screen. And there are several things that you can do. You can click on participants, which will bring up a dialog on the right-hand side showing your fellow attendees. And we encourage you to ask questions. And in order to do so, we recommend that you use the raise hand feature. On the right side, you will see a button called raise hand. And if you click on that button, I will see a blue hand symbol in my screen, which informs me that you're about to ask a question. To ask the actual question itself, we encourage you to make use of the chat feature. So at the bottom of your window, you have a balloon icon with chat written below it. If you click on that icon, the right-hand side window splits in half, brings up a chat box. And at the bottom of that box, you can enter a message, which allows you to address the nation. Or should you see a fellow participant, a fellow colleague, a family member, friend, you can also select that individual and send that person a message in private. That pretty much concludes the household notes as far as the Zoom video communication platform is considered. And that means that we're going to talk about Mapp XT, because the day before yesterday, when we had the introduction of our Precision Toolset, which you will find on the YouTube channel, Thinking Sound, in that webinar, we introduced the roadmap for the weeks to come, and we talked about the pillars of the Precision Toolset. And today, we're going to talk about one of those pillars, which is Mapp XT. And all of these tools together constitute the tool set, and that allows us to have a turnkey solution for sound system design, control, monitoring the health of our system, manage the loudspeakers, support immersive sound and spatial mixing, and even the distribution of our power, audio, and remote monitoring system signals. So that's the entire tool set. But in order to learn more about that, I recommend you watch that particular webinar on YouTube channel Thinking Sound, because today our focus will be Mapp XT. And that means that I made a checklist with topics just to make sure that I don't forget anything. And the topics of today are: what is Mapp XT? How do you register for Mapp XT? How do you connect to the Mapp XT server? We're going to look at the main graphical user interface of Mapp XT, the menu bar, how to set our measurement units, natural environment, prediction plane, layer management, right-click menu, very convenient, how to introduce visual aids such as architectural visual aids and multi-level visual aids, how to insert individual loudspeakers, how to do an actual prediction, which is what it's all about, and how to use the measurement viewer, and how to finally import graphics, more specifically computer-aided drawing graphics such as CAD files in the so-called drawing exchange file format. So that's the checklist for today. I've printed it just to make sure that I can use a very old-fashioned pen and check and make sure that that we're covering all topics. So I turn on my camera, I turn on my microphone, I press record, and we're streaming to Facebook Live. So we're in a good place. Okay. So trip down memory lane. Where did Mapp XT come from? Well, it basically started with the building of the anechoic chamber at our factory in Berkeley, California, which was in 1995. And it houses a loudspeaker positioner that allows us to rotate, to pivot loudspeakers with less than 1 degree accuracy. The build of the anechoic chamber basically initiated the start of Mapp development. And here you see Mapp, it wasn't called Mapp at the time, it was Polar TD, Meyer Polar 3D. This is the very first, or one of the very first incarnations of Mapp, which was still a prototype at the time. And this is around 1996, so 1 year after building the anechoic chamber, when John Meyer started measuring a lot. Meyer Polar 2D at the time would allow you to look at high resolution polar data with the ability to see loudspeaker interaction in grayscales, as you can see in this picture, as well as the frequency response at any point where you see the crosshairs, which is where your cursor lives. So the right window shows you the frequency response at the position in space, in the 2D map, the room map, where your crosshairs live. And this prototype ultimately was further developed into what was known as Mapp Online. And Mapp Online is around 1998. And that was unprecedented at the time. It is the world's most trusted prediction tool, and it revolutionized sound system design, specifically making the behavior of directional subwoofers array visible, because suddenly we can look at all these points in space, which gives you a phenomenal advantage. That being said, since the millennium, Meyer Sound has been looking into 3D, and I'm quite happy to inform you that we're approaching the end of the era. All of this is about to change in the foreseeable future. But that being said, we've been looking into 3D for quite some time, almost 2 decades, and also already showed in 2007 at Plaza. We showed the first interaction between 2 objects. So stay tuned for more information regarding 3D. Okay, so what is Mapp XT? Well, it's a multi-purpose sound system design tool, and it has the following key features: high-resolution sound field predictions of energy distribution in either the horizontal and/or vertical plane. It will show you headroom data and SPL data in such a way that you can ensure yourself that your loudspeaker is still within its linear range of operation. So it's not going into compression, and it's not distorting, as we're about to discover. It will show you frequency response, which consists of 2 parts. There's the so-called amplitude portion, the amplitude curve, or frequency response, also colloquially referred to as amplitude curve. And then there's the phase trace. And we show you both, and the phase trace is equally important, if not more important, and is the reason that Meyer Sound developed proprietary solutions such as delay integration, which is today part of product integration. And we discussed that at great length in a previous webinar, which you will also find on our YouTube channel, Thinking Sound. In addition, it shows you what is colloquially referred to as the impulse response, although we prefer to call it the IFFT, which stands for inverse fast Fourier transform, because it's calculated out of the transfer function. It's basically a 2nd generation transfer function. And meanwhile, we support multiple loudspeakers, arrays, and measurement positions, measurement microphones, which you can position at any point of your choosing. Finally, all of that can be arranged in layers, which we can give colors and names, and that allows us to manage our session very conveniently. There's an auto display design assist that we covered in a previous webinar, and we can import computer-aided drawings, which was also discussed in a previous webinar. Okay, and finally, we have all the processing available in our sound design tool, sound system design tool, all the processing available that one would expect from real Galaxy devices, such as delay integration, LMBC, U-shaping, so on and so forth. And one of the things that makes Mapp very powerful is the accuracy and precision, which is basically due to the phenomenal resolution of our data, which is acquired in-house. So we measure the loudspeakers in-house in our own anechoic room with a positioner that can rotate pivot loudspeaker with 1 then less degree accuracy. And those polar files, as they're known, consist of amplitude and phase data. And finally, we have a procedure for determining the maximum loudness that a loudspeaker can produce without distorting or without going in compression or limiting. And that procedure is available for you to read, and you will find it at mnoise.org. And that procedure shows you how we determine the maximum loudness, the maximum linear, which is the keyword, linear SPL and headroom data for Meyer Sound loudspeaker products. Okay, here you see a loudspeaker mounted to the positioner, and we call that the device under test, or DUT. It's sitting on top of the position arm, and the position arm is connected to two servo motors. There's a servo motor at the base of the arm, and then there's a servo motor directly behind the loudspeaker. And I think we can see that better in a short video segment that I'm about to show you. Our measurement microphone obviously also lives in that same anechoic room, and it's stationary to minimize, to eliminate measurement errors. So we're not orbiting the loudspeaker with the measurement microphone. The measurement microphone is stationary, and we're rotating the loudspeaker around a certain center of rotation during measurement, or CRDM. So this is a vintage computer generated imagery, a video, which shows you the anechoic room. So we're about to enter the anechoic room. Camera is about to swivel around, and then we see the positioner sitting in front of the door that we just came in through. Door is about to close, and now we see a loudspeaker mounted to that positioner, and that positioner with its two servo motors can rotate the loudspeaker like this, and it can rotate the loudspeaker like that. And that allows us to get very precise polar files. So those that have been watching the introduction to the tool set the day before yesterday have seen this as well. We measure those loudspeakers in 1 degree increments. That means that in both the horizontal as well as the vertical plane, we're dealing with 360 data points per loudspeaker, which is a phenomenal amount of data. This is true for the horizontal plane, plan view, when you look on top of your venue, as well as section view or cross-section when you look at your venue from the side. And all of that while using 48 points per octave resolution, which is roughly in the barely 10 audible octaves that you and I can hear. That's about 480 frequency points. So these are a vast amount of data. The trade-off for that data is that you have to go online. This is historically due to the vast amount of data and the number crunching involved. And that meant that in 1998, when Mapp Online was launched, it was required to make a connection using a patented client-server method for processing those huge calculations remotely. And that is still used today. But as I said before, all of that is about to change in the foreseeable future. So there you see some examples. We're going to look at that at great extent. So we see in the top left corner, we see our sound field prediction, propagation of sound in the room. In the top right corner, we see a so-called band spectrum, which shows me my headroom for various excitation signals, such as ping noise, B noise, and M noise. In the top left corner, I see my frequency response, which consists of both amplitude and phase. And in the bottom right corner, we see the impulse response, which is its colloquial name, even though we prefer to call it IFFT. I mix them up continuously, indiscriminately, so you have to forgive me for that. Okay, one of the first things that you need to do if you want to connect to those Mapp servers to do the number crunching is to register for Mapp XT, and that is the next thing that we're going to discuss. So in order to do that, you have to visit the website. So you go to meyersound.com, and once you've browsed to that website, you're going to select products. And that takes you to the products page. And in the products page, you're going to scroll down the list of products until you see Mapp XT, and you're going to click on Mapp XT. On that particular page, there is the option to register for Mapp XT. So you're going to click on that tab, and it will take you to a form. And all you have to do is complete that form, which means that you have to enter your email address, choose a password at your discretion, provide your first name, last name, so on and so forth. Now, it's very important to emphasize that the credentials that you're about to enter in this form are not necessarily the same credential that you use to log into the Meyersound website. Okay, and this is very often confused with another. People assume that they can register to the Mapp server using the same credentials. This is not necessarily true. So please be aware of that at all times, that you need a dedicated set of credentials to connect to the Mapp servers and do the number crunching. So once that form is completed, you will get a notification that you've successfully completed the form, and then you should check your inbox because you will receive an email containing all relevant data. Okay, once you've successfully registered for Mapp XT, all that's left to do in the Mapp XT page under products is to go to software, and there you can download the latest version for your specific operating system. So that is the steps for registering to Mapp XT. Rest assured, all these steps you will also find on the support videos on your website, which I will show you by the end of today's webinar. So let's assume for a second that we've successfully registered for Mapp and we've downloaded the program, we've installed the program, and that means that we can start using the program. So I'm gonna quit the keynote for now, and I'm gonna fire up Mapp. I already have it living over here. I'm gonna fire up Mapp, one instance, and let's see what there is to do in Mapp, what we can learn, what we can cover by looking at the main graphical user interface. So there we go. Here you see your main graphical user interface. In the top left corner, you have your menu bar, very common to a lot of applications. In the middle, we see our sound field. We refer to that as our prediction plane. The sound field has an x-axis at the bottom, which goes from 0 on the left-hand side all the way to 40, in this case, meters at the right-hand side, and from 0 at the bottom along the y-axis all the way to 20 meters to the top. So not everybody uses meters. So I think one of the first things that we should look into is like, okay, what if I don't want to use meters? How do I change that, for example, into feet? So this is how you do it. Let's go to settings. And if we click on settings, the first option at the top of the menu is so-called measurement units. Notice that all our menus also show you the hotkey combination to open that particular dialog. So let's go to measurement units, and that brings up this dialog, and that allows us to choose our distant units. Okay, if you don't want to use meters, prefer centimeters, whatever floats your boat. It allows us to choose the weight unit that we prefer to use. It allows us to set the temperature unit, Kelvin, Celsius, Fahrenheit for those that use it, and ultimately the pressure unit, pascals, kilopascals, or millibars. I'm going to leave this for what it is. I'm a European. I'm used to using meters, so please allow me to continue to do so. That being said, if you want to change those units, this is where you do it. So what comes naturally? Let's see. We've set the units for our sound field. I'm sticking to meters, and currently the sound field has certain dimensions. It's 40 meters wide, and it's 20 meters high or tall, if you will. But what if I want to resize my sound field to different dimensions? Well, in order to do that, we go again to settings. And the third option from the top is the so-called prediction plane. So let's click on prediction plane, which brings up the following dialog. Notice that in this dialog, I can enter the dimensions of my prediction plane size, which currently has a width of 40 meters and a height of 20 meters. So if I were to make this 20 over 20 meters, my prediction plane becomes a square. If I reduce the height to 10 meters, we're back at a rectangle, but this time the rectangle is not 40 by 20 meters, but 20 by 10 meters. So there you set the size of your sound field of your prediction plane. Notice, however, that to the left, we have a dialog showing two coordinates, X and Y, which allows me to position the left corner, the lower left corner, which we also refer to as the origin. So these coordinates in my sound plane dictate where the XY coordinates 0, 0 in the bottom left corner are gonna live. So maybe for whatever reason, I want that bottom left corner not to be 0 in the X dimension, but negative 10 meters, okay? In which case, the bottom left corner now lives at negative 10 in the X dimension, 0 in the Y dimension, and my origin, the 0, 0 itself, now lives in the middle of my screen. The same could be true for the Y dimension. Maybe I want my origin to live in the middle of my prediction plane, in which case I would enter negative 5, because now the lower left corner of my prediction plane lives at negative 10 in the horizontal and negative 5 in the vertical. And as a result, my origin 0, 0 lives at the center of my prediction plane. Now, depending on what you're about to do, whether you're trying to do a plan view design or a section view design, we're going to talk about that, you are free to determine where you want to put your origin, your 0, 0 coordinates, which is a function of where the lower left corner of your prediction plane lives. Of course, a square or a rectangle is always confined within 4 edges, 4 sides. And on the right-hand side in this dialog, we see that each of these sides have been assigned a number. So the top is number 1, side number 1. The right-hand side is number 2. The bottom, the floor, if you will, is number 3. And the left-hand side is number 4. And in the dialog below that, we have the opportunity to turn those sides of the prediction plane, that bounding box, if you will, we can turn that into solid surfaces. By default, they're turned off, but we could turn them into solid surfaces simply by taking each of those sides out of bypass. And notice that in the sound field, where we started out with a dashed line, which is transparent walls, that the dashed line, once I take this out of bypass, becomes a solid line, a continuous line, telling me that these are no longer transparent walls. My sound field is no longer boxed in by transparent walls. And finally, if I decide to do so, I am free to assign a certain material to those walls. 4 walls is all you'll have to play with, but it serves a purpose. It will introduce specular reflections, but we'll save that for a follow-up course on Mapp XT. For now, I'm going to turn all of this off. We have no application for this. This is an introduction. All I wanted to show you is how to change the dimensions of your sound field and how to position your origin, your X, Y, 0, 0 coordinates by placing the lower left corner at a specific position of your choosing. Okay, let's reset to the initial dimensions that we had. Notice that my 0, 0, my origin lives in the bottom left corner. Okay, that is the prediction plane. So I'm going to take a pen just to keep track of what we've been talking about. We've looked at our measurement units. We've looked at the prediction plane, how to change it. So I'm ready to start introducing geometry, and I'm ready to start introducing loudspeakers. But I would like to do so in an organized fashion. So please allow me to propose that we start using layers, because layers gives us the opportunity to organize our workflow. So let's go to tools, and let's go to settings, and let's go to layer management, which is the 4th option from the top. Let's click here, and this will bring up a dialog showing the layers. This is not unlike what you're used to see in computer-aided drawing software, such as AutoCAD or Vectorworks. Currently, we have one layer whose color is black. It's activated, which means that whatever I'm about to introduce, whether it's loudspeakers or architecture, whatever I'm about to introduce will, by default, end up in the active layer, which is currently layer 0. We have the option to make those layers invisible and visible, and we can lock them as a contingency to make sure that we do not accidentally move something or erase something. So what I typically like to do at the beginning of any design is just create a couple of additional layers. Okay, I'm creating a random amount of additional layers. And I might call one of those layers, by double clicking, I might call it main, because this is where my main speaker might end up. Another layer I might call LFC, which is our definition of a subwoofer, which is the colloquial term. This might be the layer where I end up positioning my subwoofers. I intend to use some microphones. So maybe I want to organize my workflow by making a dedicated layer for microphones. I might want to introduce some architectural aids and lines and such. So I might make a layer for visual aids, okay? And depending on what you're trying to do, you might want to create extra layers. For all you know, you intend to use a delay loudspeaker, in which case you would rename one of those layers into delay. Okay, so that is how we create layers. We are free to change the color of those layers, which means that the items or objects that we're about to introduce will have those specific colors. It's ill-advised to use red, as we're about to discover, because red is also the color that will be assigned to layers that have been locked. So if you use a red color, you might not be able to distinguish between layers that have been locked and layers that have a red color applied to them. So let's leave this for now. Okay, maybe not choose yellow. Yellow on a white background is a poor choice. So let's make that a different kind of color. But you get the general idea. That's how we create our layers. Okay, so I'm going to check the layer management. Okay, well, maybe time has come to introduce some architecture. Okay, maybe I want to introduce a stage. Maybe I want to introduce a line that represents my audience at ear height. And I think that, you know, our current dimensions are somewhat large. So I propose that we go for a prediction plane, which is maybe a little bit smaller. Let's make it 20 meters wide, and let's make it, give or take, let's make it 8 meters high. Okay. I like to see the stage personally, and that means that I like, you know, this is very common to have our origin, our X, Y, 0, 0 coordinates, typically positioned at the edge of the stage lip. Well, we yet have to determine how deep our stage is, how high our stage is. And the other thing at this point that we have to discuss is, are we doing a section view or are we doing a plan view design? Because after all, Mapp is 2D. What do I mean by that? Please allow me to temporarily go back to the keynote presentation and show you this slide, which we already saw in the introduction of the tool set, the Precision Toolset. So since Mapp is 2D, we only have 2 dimensions to play with at a time, which means that if I'm doing a plan view, looking on top of the venue, then you were looking at the plan that runs along your XY coordinates in 3D space. But if I'm looking at a section view, looking at this venue from the side, well, then I'm looking at a plane which in 3D space would be my XZ plane. And sometimes, for example, think in the round situations or arenas where you are doing 360 degrees in a round, sometimes you have reason to look at a transection. So that would be like observing the stage from front of house or observing the front of house from the stage. And we refer to that as a transection view. And that in this case in 3D space would be my YZ plane. That is something that we need to be mindful of when designing in 2 dimensions. However, rest assured, we can perfectly work in, let's call it 2.5D, by using multiple instances of Mapp, where one instance would be dedicated to plan view and the other instance would be dedicated to section view. We could even use a third instance, which would be dedicated to transection view. And sometimes you might have a balcony for which you want to use a dedicated instance of Mapp. How to run multiple instances of Mapp is something that we will discuss during later follow-up webinars that will touch upon the more intermediate and advanced stuff. For now, please allow me to suggest that we do a section view. So we're looking at our venue from the side. We're looking at a cross section. And let's start drawing some lines like we have a stage. Now, for all I know, that stage might be, on a given day, that stage might be 5 meters deep. So what if I want to have my X, Y coordinates, my origin at 0, 0 and leaving 5 meters of depth for the stage? I would go to my prediction plane and I would put the bottom left corner of my prediction plane at -5. Putting 0, 0, which is what I'm trying to convey, putting 0, 0 at the edge of my stage. So now we have 5 meters of depth to the left. So stage will be on the left, which is for you is over here, and audience will be on the right. For all I know, that stage might be 1 meter tall. And I want to draw a line to represent that stage. So in order to do that, we have several tools to choose from. And as you're about to guess, over here, we have a tool which allows me to introduce an architectural visual aid. So let's click on that tool, left click, and this allows me in the active layer, which is current layer 0, allows me to draw a line. Just click and drag, and there's your line. Okay, let's do it again. Click and drag, there's your line. Click and drag, there's your line. okay? I don't know what purpose they serve, but they're your lines. So maybe this is not such a good idea. So why don't we select all these lines and delete them? Because that's something that you occasionally might want to do. In order to do that, we go to the arrow, which is our selection tool. So by clicking on the arrow, I'm back in selection tool, and I can click off any of these lines individually, left clicking on the lines. Okay, that would be one way of selecting them. Or I can select and drag a bounding box and select all those objects at once. And all that's left to do is right click, and that opens up a menu, and in that menu there's the option to delete those lines that we just created. If you remember the shortcut, then it's Command E on a Mac. Don't ask me for Windows, because I wouldn't know. Okay, so let's delete those lines and let's start drawing a line in another way. Because right now I used the tool to draw those lines, but maybe I want to be a little bit more specific. Maybe I have certain XY coordinates in mind that I want to use rather than drawing a line by hand. Well, in order to do that, we can do it in two ways. We can go to the Insert menu, and at the bottom of the Insert menu, there is the option to insert a architectural visual aid. That would be one option to do. This brings up a dialog, and it says, you are about to insert a visual architectural aid. Okay, do you want to label it? Sure, why don't we call it stage by typing stage? Maybe I want to put this in any of those layers that I created in anticipation of doing a design. Maybe I want to put this layer in my layer visual 8, okay? I could activate it as a listener plane for autosplay, but that's beyond today's scope. If you want to know about autosplay, be sure to watch the autosplay webinar, which you will find on YouTube. So the listener plane, we're going to leave that for another day. Since a line is a segment between 2 points, there's a first point and there's a second point, and both would need XY coordinates. So maybe my stage starts at 0 meters at my origin in the horizontal, and maybe it's 1 meter tall. That would be the first point. We know that the stage is 5 meters deep. In this case, it would be -5 meters because we start with a first point at 0, 1. And it's still 1 meter tall by the time you make it to the back wall. So there you have your first 2 points, X and Y coordinates. And if I now press OK, then we will see that line. It's automatically selected, but there we will see that line that we just introduced very precisely using X, Y coordinates. So that's one way of doing it. Another way of doing it is by anywhere using the selection tool in your sound field, pressing right click. If you press right click, we see the right click menu, and also there you will find the option to introduce a architectural aid. Brings up the same dialog with the same options. So line, segment connected by 2 points, each with their XY coordinates. Is there another way of doing this? Is there another way of doing this? Yes, there is. And that can be done in the following way. Rather than doing XY coordinates for both points, I could also say, maybe for whatever reason, I have a line that starts over here in space, but rather than assigning the coordinates of the second point, we can use polar coordinates. Let's make this level. Okay, let's make this level for now. And this is the length of the line segment. So polar coordinates give me the orientation of the line segment, whereas meters give me the length of the line segment. So right now we have a line which starts at 4, 4 XY coordinates. That's the first point. And the second point is determined by the orientation and the length of the line segment. So if I now press OK, then nothing happens, which means that I must have made an operating error or not. I did it right. So there we have the line. This is my first point. That's my 4, 4 XY coordinates. This is 5 meters long, and it's pointing, for you that would be this direction, it's pointing 0 degrees. It is level. So watch what happens if I select my line by dragging or clicking on it, right click on the menu and choose edit the properties of that line. Brings up the same dialog, Let me drag that over here. Notice what changes if I, for example, make this 45 degrees, then the line will still remain 5 meters long, but now it starts to rotate counterclockwise, and it's now pointing up at a 45-degree angle. If I make this 90 degrees, then it looks at 12 o'clock. If I make this 135 degrees, then it looks at between 10 and 11. And if I make this 180 degrees, then you shall not be surprised that it will look at 9 o'clock. So that is another way of drawing lines with very defined length and orientation. Okay, so that would be another way of drawing this line. So let me hide this line. Let me delete that line by clicking it and saying delete. And let's make sure that the new line, which is also 5 meters long, let's make sure by editing its properties that it ends up in the same position. It already has the appropriate length. It's already pointing in the right direction. I just need to make sure that its x coordinate lives at 0 and that its y coordinate is 1 meter to represent the height of my stage. So there you have your two ways of introducing lines, which is something that I use very often. Okay. Maybe it's also prudent to draw a line which represents the ears of the listeners at ear height. For ear height, I typically use 1.7 meters, and for all we know, today's audience might start at 2 meters distance. So several ways how we can do that. We can do it roughly by saying, okay, maybe this is where the audience lives, click and drag, and then I can polish it if I desire to do so by selecting the line that I just drew, right click, brings up the menu, go to edit the properties of that line, and now I can really position those values very specifically. For all we know, it starts at 2 meters because there's an egress area between the edge of the stage and the start of the audience. Ear height would be 1.7 meters. And again, I have two options. I can enter the coordinates of the second point, making this 14 meters and 1.7 as well. That would be one option. Or I could say, that line length must be 12 meters. It's a flat audience plane. It's not a rising audience plane. And therefore, I will leave the angle at 0. Both would amount to the same effect. Notice that if I click on this line, that it doesn't live in the right layer. Okay, because when I entered the line, I forgot to assign it to a specific layer. So how can we fix that? Should you discover this? How can we fix this? We can go to the properties of that line and relocate it to visual aids. That would be one way of doing it. Or another way of doing it would be by simply clicking that particular object and then putting it in any of the layers that you want. Now it's back in layer 0, and we can see that by looking at the properties, layer 0. And I can now also, provided it's selected, I can also relocate it to the visual aids layer once more, provided it's selected. So now it lives, if we look at the properties, now it lives back at visual aids. And that goes for loudspeakers, for microphones, goes for all these things. Let's make sure that our stage lives in the proper layer. So we want to have that also in the visual aids layer. And I don't want to mess with this anymore. So I'm going to lock it at this point so that I do not accidentally change it. In order to do that, remember, we have to go to our settings, layer measurement. And now we have the option to lock that layer. And notice what happens. The moment that I lock that layer, it becomes red, which is the reason why red would be an ill-advised choice for coloring any of your layers. That being said, once it's locked, I can no longer mess with it. I cannot select it. There's also the option to hide that layer. Okay, if I have a reason to no longer want to see that, I can hide that layer, but I'm going to lock it for now. I think, save early, save often. I think it's prudent to maybe save this session at now. Well, that is very straightforward. You can operate a text editor. You can operate Mapp. If we go to our file section, we have common options where we can start a new project, we can open an existing project, and of course, we can save our project. So let's save this project and let's call it a live Zoom session plan view, okay? Notice that it's a zip archive. It's a zip archive that contains an XML with the actual project. But why is it a zip archive? Because it could very well be that you're using CAD drawings as imported CAD drawings into your project, and those will then be stored as well within that same zip archive. So save early, save often. So we have our stage, we have something that represents our stage, we have a line that shows us where our audience lives. I think time has come to insert a loudspeaker. That being said, before we're going to insert a loudspeaker, there's one more way which is very convenient for introducing lines, and that is the so-called multi-level visual aid. And in order to make you appreciate that, let's go quickly back to the keynote and show how that would work. Imagine that you have a rising audience plane, and you do not have specific XY coordinates. There's no CAD drawing, there's no cross-section for you to consult. How could you still draw a line that represents the ears of the audience, seating height in this case? How could you do that? Well, another way of doing that would be the so-called multi-level visual aid, in which case you would use a laser rangefinder that allows you to measure distance, but also has a inclinometer in it. So it also allows you to measure up angle or down angle. And you would document the angle as well as the length to the first point, which in this case would be the first row. And then you document the distance and the angle to the last row. And this gives you 2 data points. Each data point has a distance and a orientation assigned to it. And once you document those, you can introduce those in Mapp as well. And the way to do that would be to either go to Insert, where you can insert the multi-level visual aid, or right-click anywhere in the sound field and choose it from the right-click menu. So let's insert multi-level visual aid. We can give this a name. For all we know, this is audience, but it's rising today. And now I can put it in a layer, which for all I know might be the same visual aid layer or any other layer of my choosing. And what I need to do is tell the Mapp prediction software, where was the laser rangefinder with its inclinometer, where was it in space, because it needs to know where you had your laser rangefinder on the tripod. So for all we know, it was at 1 meter and at 2 meters height, very high tripod today, but never mind. So that's where the laser rangefinder was, that's where my inclinometer was. And now I need to introduce that angle that I measured to the first row, which was maybe a 5-degree down angle, 1 meter distance for all I know. And I need to introduce that angle to the last row, which for all I know was a 15-degree upward angle. And the length or the distance to that last row, for all I know, was 14 meters, okay? If I've entered all those parameters and press OK, we have a new line using the multi-level visual aid, which is very convenient for larger spaces where it's either a lot of walking or using a laser rangefinder. I don't need this line, so please allow me to delete it for now. I've memorized that if I press Command E, that I can delete that layer. Okay, so far so good. That takes care of my prediction plane measurement units. Okay, we've talked about that. Time to introduce a loudspeaker. So, many ways of introducing a loudspeaker. The obvious one is to go to the Insert menu, and then there's a lot of things that we can insert, and during the course of these webinars, we're going to discuss all of them. We can insert flown loudspeaker systems, we can insert ground stack loudspeakers, including subwoofers, as we're about to discover. We can introduce horizontal arrays, such as JN1Ps. We can introduce gradient flown subwoofers. We can, of course, do the same for ground stacked subwoofers, but we'll save that for another day. Or we can insert an individual loudspeaker, which is the very thing that I'd like to do today. So let's insert our individual loudspeaker. Dialog opens up. You're about to insert an individual loudspeaker. Would you like to label it? Yes, because for all I know, this is my main PA. So let's call it mains, okay? It would be prudent to assign it to the layer that I deliberately made that houses the main speaker. So I'm going to put it in the main layer. And then we have some things that, you know, is already anticipation of the real world, because we're very likely going to use a Galaxy device to calibrate and voice our system. And those Galaxy devices have addresses, physical addresses, or addresses that identify the Galaxy device. And every Galaxy device has as much as 16 outputs, depending on the model. So here in my virtual world, where I have the same signal processing at my disposal as in the real world, I can already start to connect this loudspeaker to its Galaxy device and to its specific output on that particular Galaxy device. We're not going to do that today, it's beyond today's scope, but I want to make sure that we understand all options in this dialogue. Then I've properly labeled my loudspeaker. Now I have a drop-down menu which allows us to choose from all loudspeakers in the Meyer Sound portfolio. That's to say the vast majority. Starting with Leo family products at the top of the list, Leo M, Lion M, so on and so forth, Lena. Then we have our Ultra series, which have our UPQs, J1Ps, UPAs, Ultra X40. And if we go all the way down the list, then sooner or later we're going to get Cine Studio like Asherons and Amis, which is for cinema and studio and post-production. Then we have the LF series, which contain our low frequency control elements, such as the 1100 LFC, 900, 750, so on and so forth. USW210P new subwoofer, very exciting. Beam series, which are the so-called sound beams, and then even the legacy products and discontinued products at the bottom of the list. If you're doing cinema, you know that your screen channels might end up behind a projection screen, and we even take into account the effects of those projection screens depending on make and model. I propose that today we stay with the Ultra X40, which is a loudspeaker with 110 degrees in the horizontal plane and 50 degrees in the vertical plane. So there we see a preview of our loudspeaker enclosure, a pictogram, if you will. And then to the next of it, to the right of it, there's cabinet orientation. And cabinet orientation matters because Mapp has no way of knowing whether you're about to design plan view or whether you're about to design section view. But most loudspeakers live in portrait mode. So in section view, this is probably how you would want the loudspeaker to live. But in plan view, where you look on top of your venue, you probably want to look at the loudspeaker from above. So it's the cabinet orientation, which is mission critical, depending on whether you are working in section view or whether you're working in plan view. That being said, Ultra X40 has a rotatable horn, and sometimes due to logistical reasons, I have no chance of deploying a loudspeaker like this. I have to deploy the loudspeaker like that. Might be a center fill for all I know, pointing down at the start of the audience, and then I would still use this orientation even though I'm working in section view. So as always, it depends. It depends whether we want to look at our loudspeaker horizontal or vertical. There's also the option to invert our loudspeaker. In the vertical, that would mean mounting the loudspeaker upside down. So now my home button is over here, but now my home button is in the top. That would be flipping the loudspeaker upside down. And the same is true in the horizontal. Although in the horizontal, you're now looking along the Z-axis into the computer screen, into the third dimension. So there's very little to see at this point. So let's keep it in its default orientation, horn in the top, not in an X40 in this case, because it's a concentric design, but for a UPJ1P, for example, it would be horn in the top, direct radiated and bottom. So that's the cabinet orientation, which matters for whether you're designing in plan view or in section view. And then, of course, we need to position our loudspeaker in space, and for that, we need to position its so-called reference points. And there's two to choose from. There is the CRDM, which is selected by default. Now, what is the CRDM? That's an abbreviation for center of rotation during measurement. So that's basically the pivot point where the loudspeaker was being rotated in 2 dimensions when it was living on the positioner in the anechoic room. So let me bring back this picture to jolt your memory. That loudspeaker, where it was rotated in the horizontal and in the vertical, that point, these axes, if you will, that is known as the center of rotation during measurement. And that is default, the default reference point for that loudspeaker. Okay, so there's also another option, which I will show you in a while. So let's position this loudspeaker at 4 meters X and 4 meters Y. Sometimes you have reason to tilt the loudspeaker to steer the sound where it needs to go, which is in the audience and away from the plaster. And the steering or the tilting of the loudspeaker can be done with the rotation about that same center of rotation during measurement. And that means that, like before with the line segment, that if we go increasing values, then we go counterclockwise, which is in this direction. And if we do negative values, we go clockwise, which is in the opposite direction. So this allows me to tilt the loudspeaker, which is true in vertical, but also true in horizontal. So here we can tilt the loudspeaker. I'm going to show you another way to achieve the same effect. Okay. Other than that, we see where the center of gravity lives in space, and we see what the weight of the loudspeaker is. So let's press OK. There we have our loudspeaker, and notice that at the center of the loudspeaker, there's a cross. It's hard to tell because we have this line protruding out of the loudspeaker. We call this the center line. I call it the laser, and it's showing me in which way the loudspeaker is pointing. If I don't want to see that, then at any time I can turn that off by simply going to View and saying, pretty please with sugar on top, do not show me the center line. Now the center line is gone. Now you see it. Now you don't. So there we have a cross. And that cross, its location is at 4 meters X direction, 4 meters Y direction. So where we see that cross within that loudspeaker symbol, within that pictogram, that cross corresponds to these X, Y coordinates, if we reference our point with respect to the center of rotation during measurement. However, there's also another option, which is that we can use the front of the loudspeaker, okay, which is where the grill is, the loudspeaker grill is. And notice that if I give those, notice that there's an offset between the front of the loudspeaker and the center of rotation during measurement, because that black cross, that is where the center of rotation of measurement lives in space at 4, 4 XY coordinates. But the front of the loudspeaker, the grill is of course removed from that point. It's slightly more into the house, slightly more towards front of house. So if I were to put this at 4, 4 and press apply, you shall not be surprised that it moves the loudspeaker a little bit back, because now the baffle lives at 4 meters into the room rather than the center of rotation during measurement. By default, it's always set to center of rotation during measurement. Let's click plus. And that pretty much concludes all these parameters, okay? You can label it, you can put it in a specific layer, you can assign it to a specific processor and an output on that particular processor, okay? And then you can change the orientation of your loudspeaker. You can position it in your prediction plane, and then you can rotate the loudspeaker at your discretion. I'm happy with this. Let's do apply close. Now, for all I know, I don't want that loudspeaker to live over here. I want that loudspeaker to live somewhere at a more plausible position. Well, all I have to do is select my loudspeaker and click and drag. And now I can move this loudspeaker about freely. Imagine how cool it would be if you could do this in the real world without, hurting your back. So for all I know, that loudspeaker today is gonna live over there, okay? I just drag it there, okay? It still lives in its same layer, okay? It has the same color that we assigned it to that layer, but now we have the loudspeaker living over there. I want to see that center line once more because I want to see whether I'm sending the sound to where it needs to be. So how can I rotate that loudspeaker without using the Edit Individual Loudspeaker Properties dialog? Okay, is there another way, more intuitive way that I can rotate this loudspeaker other than using this slider? And the answer is yes, by simply using the rotation tool. If I click on the rotation tool, notice that we get a center of rotation. By default, that center of rotation jumps to the center of rotation during measurement. But I can put that position or that center of rotation, I can put that anywhere I want by just left clicking within the sound field, okay? So that is what I can do. By default, it goes to the center of rotation during measurement. And now all that I have to do is left click on the loudspeaker, anywhere on the sound field, apologies, left click and drag. I'm left click and dragging, and as I'm dragging, you notice that we're changing the orientation of the loudspeaker. It shows me the absolute orientation between parentheses, and it shows me the relative orientation with respect from where I came. So let's introduce, for example, about 6 degrees down tilt. Okay, I let the left mouse button go. If I now click once more and drag, notice that now my relative value is 6 degrees up, but my absolute value is level once more, which is very, very convenient for reasons as we're about to discover. So I think it's prudent to send the sound where it needs to go, which is probably somewhere at the most distant position, which is vertical top, as we saw in autosplay, which is the last listener on my audience plane. Okay, I'd like to know where the fun begins. I would like to know in the vertical where the sound starts. Is there a way that I can help myself? Sure, there is a way that I can help myself. I can draw a line starting at the loudspeaker, okay, make it an arbitrary length. I'm going to select that line, okay, and now I can rotate that line. Now, the line is selected. You cannot see it because of the center line obscuring your vision. So let me hide that center line. There is the line. Notice that it's dashed. It's no longer continuous. It's dashed. I can rotate that line as well. By default, the center of rotation jumps to the geometric mean of that line. But again, I'm free to put that point anywhere I want, including at the center of rotation during measurement of the loudspeaker. And now I can pivot this line, rotate this line, and notice that, you know, if you have 50 degrees of vertical coverage, I can rotate this relatively, mind you, relatively by roughly -25 degrees, which gives me half of my vertical coverage angle. Something that you will be able to appreciate if I bring up the center line, the laser protruding out of my loudspeaker. And that's very convenient because now I have a line which shows where my loudspeaker is pointing, and I have a line which shows the bottom edge of coverage. And if I want, I can rotate both by simply selecting the loudspeaker and the line at once, go to the rotate tool, and make sure that the point of rotation lives at the loudspeaker. If I now left click and drag, I'm rotating both the center line, which shows me where the sound is being sent, as well as the edge of coverage, the bottom edge of coverage in the vertical. So, very convenient way to make sure that you send the sound where it needs to go. Save early, save often. I would like to see how this behaves, whether I'm doing anything sensible. I'm ready to do a prediction. I want to see the distribution of energy in this prediction. But the predict button is grayed out. It's grayed out. I can click it all day long, nothing will happen because, lo and behold, in the bottom left corner, it says your server login status is online. And remember, we need to be online. We need to be connected to the server to do any predictions because the number crunching happens in the factory. So the red padlock in the bottom left corner is telling me you are not connected to the server. And if you're not connected to the server, you cannot do any predictions. So we need to fix that first if we want to see any predictions. So the problem that we're dealing with is that we're getting a message telling us that we're no longer connected and that we have to log into the Mapp server via the settings menu, in which case, hopefully, that padlock will turn to blue. Well, these are the credentials that you entered. These are the credentials that you entered in the register for Mapp form on the website, which we saw at the beginning. So let's go to settings, and all the way in the bottom, there's the option to log into the Mapp XT server, which brings up the following dialog. Okay, so the email address that we used was example4mappxt@gmail.com. This is what I entered in the form. The password is known to me. I'm going to press login, and in the bottom left corner, you will see that my red padlock has changed into a blue padlock, and it says we're online, which means that we can predict. And in the top left corner, you see that my predict button is no longer grayed out. And now you have about 20,000 frequencies to choose from, to look at. Recommendation is look at those frequencies where the loudspeaker is steerable, where it's a point and shoot loudspeaker, which is not at low frequencies where most loudspeakers are virtually omnidirectional. So our recommendation is that you'll typically end up looking at a 1 octave wide interval, okay? It doesn't have to be 1 octave wide interval, it could be 1/3 octave, 1/6 octave, but in general, 1 octave is perfectly justifiable. A 1 octave wide interval. And then there's several frequencies to choose from where this octave is centered, okay? So why don't we look at 4 kilohertz? We know for sure that at 4 kilohertz, the horn is control, which will allow us to see whether we're sending the sound where it needs to go. So if we now hit predict, we're going to look at a 1 octave wide frequency span centered at 4 kilohertz. So there we go. Let's press predict. Okay. So now we see the distribution of energy within our sound field. And the first thing that we need to talk about is about the scale and what is it that we're looking at. Because this mode is known as attenuation mode. We're looking at attenuation over distance. We're looking at propagation losses over distance. And the scale is shown at the right-hand side. These are so-called jet colors, where red is loud, as in hot, whereas blue is cold, as in soft. And the loudest position, like in the real world, is most likely at 1 meter distance when you're staring into the loudspeaker, into its throat, into the loudspeaker, on access to the loudspeaker. That is typically where it is at its loudest. So in Mapp, the sound plane is always, sound field is always normalized to the loudest position in the sound field, which is typically on access to the loudest loudspeaker or the loudest array in the sound field. So this color is 0 dB SPL, okay? And then, of course, if you increase your distance, the inverse square law will make sure that SPL loses market share. So you go from hot, loud colors, you go to blue, cool, soft colors. You should also notice that there's a circle of 1 meter radius where we do not see a prediction. This is the circle of inclusion, because with every loudspeaker, you need to respect a minimum distance for it to become a single coherent source, especially for loudspeakers that are built out of multiple transducers, multi-ways, that do not occupy the same point in space. So within a 1 meter radius for all products, you will not see a prediction, because within a 1 meter radius, it hasn't become a loudspeaker yet. It hasn't matured. You need to respect the minimum distance. However, outside that 1 meter radius, you will see a very accurate prediction. Right now we have these gradient colors, and it goes from 0 to -42. If I make our prediction plane a little bit larger, so that you can see a little bit more of your surroundings, let's make this 40 for a while, and let's make this -10, so that we can see a little bit more of our surroundings. If we now predict once more, then you see that once we go off the scale, that we have the same color blue everywhere, okay? Does not mean that in this region, the loudspeaker is running at the same level, but you're looking at levels that are below 42 decibels with respect to full scale, where full scale is the loudest position in the sound field, which is at 1 meter distance on access to that loudspeaker. So it's not that my level over here remains constant, it's just that you're looking at values which are below -42 decibels full scale. If I want to see more detail over here, I am free to go to settings. And if I go to settings, then there's the option to set my SPL range. This determines the scope, the extent of that scale. By default, it goes to 42, but maybe I have a reason to increase this value because I want more detail, in which case I can set it to 72. If I set it to 72, okay, sure, I'm making an operator error. If I set it to 72, oops. If I'm setting it to 72, then the scale will be updated. 0 remains 0 full scale, but now that threshold where we go off the scale no longer lives at -42, it now lives at -72. And then you see what purportedly behind the loudspeaker looked like the same level is far from being the same level, because my scale is now much larger. I therefore see sounds which are much softer, below the default setting of -42. I'm going to change that back to the default setting, but this is where you can reveal more detail at lower levels, more specifically. What else can we do with this picture? Well, maybe I don't want to see a continuous scale. I mean, it serves a purpose because the sound system that looks the prettiest sound the best, but maybe I have a reason to change that scale to discrete steps. And I can do 64 colors rather than 256, or 1 color per dB, or 1 color per 2 dB, or 1 color per 3 dB. So let's look at 1 color per 3 dB. If we use this setting, we see that our scale on the right-hand side certainly is no longer a continuous scale, but is now a scale in discrete steps. Every 3 decibels, we see a change in colors. And in the auto splay webinar, which you will find on YouTube, I explained that this serves a purpose. So let's restore the dimensions of our prediction plane, the dimensions that we had before, so that we're back at the original scale that we had. So there we have those colors. And what that means is that every time I go from one color to the next color, that I make a 3 dB step. If I go from this color to the next color, I make a 3 dB step. And if I go from this color to the next color, I make another 3 dB step. And if I go from this lime color to this cyan color, or whatever you call it, then it's another 3 dB step. The contours, because that's what is known as, this is a contour chart or an isobaric chart, the contours, the lines that separate the colors from each other, are the positions of equal loudness. So everywhere we see this line separating this yellowish color from this lime color, that line are positions from equal loudness. And that shows me that if we call this yellowish color 0 dB, that we lose 3 decibels over here and we lose another 3 decibels over here. So I've aimed my loudspeaker in such a way that from vertical bottom, look at the YouTube webinar autosplay to know what that's about, from vertical bottom to vertical top, that's within 6 dBs, and I would be happy as a clam in high tide. If you feel that it's a little bit too loud in the front, well, if we increase the distance to that loudspeaker, more distant is softer. Is there a way how we can do that? Yes, that is the rotate tool. Let's select our center line and that vertical line, that line that represents the bottom edge of coverage, and let's pivot this configuration, but instead of doing it at the loudspeaker, let's do it at its destination. If we do it at its destination, I can now rotate that loudspeaker and its bottom edge of coverage, okay, and can put it up a little bit in the air. I will lose a couple of meters in the front, but I can put it up a couple of meters in the air, additional meters, and then you will see that I now get a deceleration as I walk into the room. So that rotate tool is super useful. However, sometimes you might have reason to look at something really specific. Sometimes you might want to zoom in. And that's where our 4th tool comes into play, which is the magnifying glass. Okay, if I click the zoom tool, what I can do is click anywhere, left click in the sound field, and that will allow me to zoom. If I press Option left click, then I can zoom out again. Left click only, zoom in, Option left click, zoom out. Okay? Another way what you could do is say I'm going to drag a box with the magnifying glass about the area of interest. Notice that I've now zoomed in on this particular region. Command 0 will restore the view, which you can also see from the view menu. If you press Command 0, then you zoom out to your drawing plane, your prediction plane. You might have a reason to see how the loudspeaker is behaving with respect to the stage. Well, then you would drag with your magnifying glass on that particular area and look at that particular area. So that's your zoom tool. Maybe you want to look, maybe you want to look at a specific part in the audience, then you would zoom at that. Okay, speaks for itself. Okay, so that is the 4 tools. We've looked at predictions, we looked at the bandwidth of our predictions, we looked at layers, we looked at 4 kilohertz. We made sure that we were connected to the server in order to do our predictions. Now, let's look at one more picture over here. Notice that we're looking at 1 octave centered at 4 kilohertz, and all of that information is shown in the bottom screen over here. It tells you that you're looking at a 1 octave interval centered at 4 kilohertz, which means that the frequency span that you're looking at is roughly from 2K8, so 2800 hertz, all the way to 5K7, so all the way almost, so roughly from 3 kilohertz to 6 kilohertz. That is the interval that you're looking at, and it shows you over here. To its left, we also see that air attenuation, which is penalty points, it's the attenuation of high frequencies as you increase your distance, that air attenuation is turned on. And it's set to specific thermodynamic values, which is a room temperature of 20 degrees Celsius, a certain atmospheric pressure, and a certain relative humidity. This will affect the propagation of high frequencies, which are subject to air attenuation. And sometimes you might have a reason to not want to see that, in which case you can turn it off. If you do not want to see the effects of your real environment, you go to settings and you go to natural environment, okay? And this is where you can turn it off. What I would give to be able to do this in the real world, like turn off air attenuation of high frequencies, probably would also mean that there's no more air, and that would pose a much bigger problem. But this is where you can turn it on, and this is where you can turn it off. This is also the dialog where you would set your room temperature, the humidity on a particular day, and the atmospheric pressure. Sure, there are some different regimes, whether you're below 800 meters or above 800 meters, but below 2 kilometers or above 2 kilometers. We'll save that for another day. But sometimes you might want to turn off air attenuation, in which case you will not see your high frequencies being penalized by air absorption. So that's where you turn that on and turn that off. Okay, well, that means that we have done a lot of stuff. What else is there to see? Sometimes while I'm drawing, I might want to know where my cursor is within my environment. In order to do that, we can go to View. And if I go to View, there's the option to show the so-called cursor coordinates. If I enable this option, notice that between parentheses, I always see the XY coordinates of where my cursor is in space. So sometimes, you know, somebody asks you, where does the loudspeaker need to be deployed? Where does its center of rotation during measurement live? This is one way of getting in the ballpark and saying, well, it's roughly, you know, 16 centimeters behind the edge of the stage, 4.7 meters up in the air. Or how high is the stage? Well, the stage is about 1 meter high. So that is where that option comes into play. If you want to work in a more precise method, there's also the option to use a grid, in which case we want to set the grid resolution from off to, for example, coarse, medium, or fine. If we set it to fine, then we get a grid every 1 meter at this scale. Notice that the color of this grid by default is black, but if you have reason to change that color, then here is the place to do it. If you'd rather look at a purple grid, or whether you look at an orange grid, this is where you set the color of that grid. The density of the grid is set under settings, grid resolution. So that's where you set your grid, and that takes care of that. Okay. So what else is there to do? We've already looked at file, introducing new projects, open projects, saving projects. Sure, that takes care of that. I want to wait a little bit with importing graphics, because there's one more thing which I would like you to see, and that is I want to see a microphone. So let's go to the microphone layers and introduce a microphone. Again, there's two ways that we can do it. We can go to our insert menu and click insert microphone. That would be one way of doing, or right click anywhere in the sound field and go to the insert microphone dialog. Insert microphone dialog brings up something which is remarkably similar as insert loudspeaker, except that this is now my microphone, okay? In a SIM ecosystem, we can use multiple of those living on so-called mic switches that have an address and up to 8 input channels. That's beyond the scope of today's webinar, but this is my microphone. I can give the diaphragm, not to be mistaken for the base of the tripod, but where the diaphragm, the pressure sensor lives in space, I can give that coordinates. And for all I know, I want to measure at ear high, into the room, let's say somewhere at 9 meters, 1.7 meters high. I want to measure at ear height. I can rotate the microphone. I do not see a reason why you would want to do that, because they're omnidirectional typically. So you might want to leave that alone. And of course, if you're doing section view, you would be looking at your microphone like this, whereas if you're doing plan view, you would be looking on top of the tripod. And then you probably want to orientate your microphone like that. So I'm going to keep it like this. I don't want to turn it upside down, okay? And I'm going to press OK. There is that microphone. If I now do a prediction, then I not only get the distribution of energy through the room, but we can now also look at headroom, transfer functions, impulse responses, amplitude, and phase. And in order to do that, we go to Tools and we go to the Measurement Viewer. And the Measurement Viewer shows us three tops. There's the headroom top, there's the IFFT, colloquially referred to as impulse response, and then there's the frequency response. Let's make this a little bit larger. Let's give this a little bit more real estate. So this is the so-called headroom, which shows you third octave band spectra. And it's important to know that currently we're looking at headroom for pink noise. There's also other noise signals such as B noise and M noise, which we will discuss at a later point. But here you see the headroom. This shows you the potential, the remnant that is left over, okay? Before we see the onset of compression or distortion. Most people will be interested in these figures, which shows you your average, or your average SPL, A-weighted, C-weighted, and Z-weighted. Z-weighted is zero weighting, no weighting filter altogether. And it shows you your peak value. For reasons beyond the scope of this webinar, there's a 12.5 dB difference between average and peak. That has to do with the crest factor of pink noise, for which you should consult mnoise.org. But this shows me how loud this loudspeaker is at the current distance to the loudspeaker. So we can see that the distance between the microphone and the loudspeaker is roughly 10.7, 11 meters, give or take. And at that distance, this loudspeaker does, let's round it up to 98 dB on average at 11 meters distance. So this is something that we should look into in great detail in future webinars. The second top is the IFFT, or so-called inverse fast Fourier transform. Let's right-click and make this as large as possible. And then we see the impulse response. This is the point in time that the sound out of the loudspeaker arrives at the microphone that lives at a distance of roughly 11 meters. We're going to talk about this at great length, but those that use analyzers such as Smart and Sim are looking at data like this constantly. Finally, let's go to our frequency response, which is the third top, and let's look at the room result. Now, if you were to see this in the real world, for those that use analyzers, they would instantaneously know that they forgot to do something, which is to synchronize for the time it takes for the sound to cross the distance between loudspeaker and microphone. Because our loudspeaker lives at a distance of roughly 11 meters to the microphone, and the sound doesn't cross that distance in zero time. So those that use analyzers such as Smart and Sim, they would set their delay locator, and that would take care of that. That would delay the reference signal, allowing the measurement signal to arrive in time as well. And then we see the amplitude response, which is functionally flat, and we see the phase response. We see similar data with or without smoothing, as you would expect to see in an analyzer. And we can store all of that and recall all of that, and that's about the last thing that I should do today, which is I can store this trace, I can store this live trace. A dialog opens up informing me that I have stored a response. I can label this, and I can say this is at the front of house position, okay, where I measured the X40 solo, which tells me that I was only measuring the X40 at the front of house position. I can put that in a memory slot by selecting that memory slot and recall it, and then it says, are you sure that you want to put it there? Say yes, and now that trace lives over here in memory slot where I can, memory slot A, where I can consult it later for future purposes. I could also select any of those stored traces from the down menu in that particular slot. That pretty much concludes the introduction. In future webinars, we are gonna apply this tool time and again to design our sound systems in such a way that we are confident about the performance of that sound system. Which leaves one more thing to look at, and that is importing graphics. And then we should quit because we're already at 1 hour and 20 minutes. Boy. Okay, What if I have reason to import a graphic? Ah, we have a hand. Somebody raises his hand asking a question, which would be Precision Entertainment. Grow for Precision Entertainment. Please use the chat to ask your question. Okay. My ETA does not show phase. What have I done wrong? Your RTA, but band spectrum is time blind. So in band spectrum, you will never see, in band spectrum, which is a single-ended FFT, which is, you will never see, sorry, in band spectrum, you will never see phase because band spectrum only shows you the energy per third octave interval. You only see phase if you leave the headroom top and go to the frequency response top, which shows you the transfer function, which is dual channel FFT rather than single-ended or single channel FFT. Okay, so one more thing. Let's start a new project. I'm going to save this, but let's start a new project. There is a webinar on the YouTube channel where we see Cuauhtemoc Mendez prepare DXF files of CAD drawings. Okay, so if you want to know how to do that, you should go to that webinar. But suppose for a second that we have a drawing which has been prepared, which is fit for Mapp, ready for Mapp. How would I import that drawing? Well, in order to do that, we go to File, we go to Import, and there we can import our graphics. All that I have to do is go to the folder where my DXF cut files live, my drawing exchange file, okay, which we cover in a different topic, how to prepare these, but let's assume that they're there, they're ready to go. Depending on whether I'm doing a section view or a plan view, you want to choose the appropriate DXF. You're going to click on Open, which brings forward a dialog. Now, in this preview, we see the entire CAD drawing, which is larger than the room of interest. However, the room of interest is indicated by these red brackets, and that is the area that we want to have as a background in our prediction plane in our sound field. You have to know the units that were used in the DXF, which is meters, and then there's 3 options to choose from. I'm going to use the drawing limits that come with the graphics file. I'm going to use the drawing limits that come with the graphics file. I'm going to say import graphics, bada bing, bada boom, and there is my DXF file ready to go. All that I have to do is introduce a loudspeaker. Okay, all I have to do is introduce a loudspeaker, and we can, start pointing and shooting and see when a loudspeaker, suspended from a truss somewhere over here, aiming at the last row. We can start looking at how that would work. Okay, this would be section view. You would repeat the same steps for plan view. So if I were to do a new project for plan view, I would go to my import graphics. Rather than choosing the section view, I would choose the plan view, which gives you the venue as seen from above. I would use the drawing limits from the graphics file. Be sure to watch the import CAD drawing into Mapp webinar, and then you see your venue from above. We're going to discuss that at great length in future webinars. But I think it suffices for now. Okay, let's go to the checklist. Let's make sure that I've talked about all topics that I wanted to cover today and make sure that I did not forget anything. We talked about what is Mapp XT, how to register, how to log in. Otherwise, you cannot make any predictions. We looked at the main graphical user interface, the menu bar, how to change your measurement units from meters to feet and kilograms to pounds, how to turn off the air, as I like to say, how to turn on your natural environment or turn it off, how to change the dimensions of the prediction plane, how to work with layers, the right-click menu, which basically has a subset of all options that you can choose from through the regular menu bar, how to introduce lines such as architectural aids or multi-level with help of a laser or a laser and inclinometer, how to insert a loudspeaker to do a prediction. We started looking at the measurement viewer, which we will continue to do in future webinars, and finally how to import graphics. Well, I think for now that suffices after 1 hour and 25 minutes, which means that I'm willing, to spend a couple of more minutes to talk, to address any of your questions, should you have them. Okay. You joined late. This webinar will be uploaded on YouTube channel. Yes, as always, these webinars will be uploaded on YouTube. So if you go to YouTube, Thinking Sound, that is where you will find this webinar within the next couple of hours. We enjoy almost 9,000 views, which is awesome. And that leaves me to inform you that next Monday, we're going to do an introduction to Compass, because Compass and Mapp are the tools from the Precision Toolset that we use very often. We're going to look at Compass, and then next week we will have our first case study. So we're going to look at an actual example of how to apply all these tools. Okay, I think that brings us to the end of today's webinars. Sorry for going over time a little bit. These topics are very involved, and we're committed to making sure that you get the most out of this. So I suddenly realized that what I just showed you, I did without sharing my screen. Okay, so let's do this exercise once more. Yes, you will find this video on YouTube, okay, on the Thinking Sound channel with almost 9,000 viewers. And next Monday, we will have a webinar called The Introduction to Compass, which is one of those other pillars of the tool set that we use. And then we will also discuss our first case study using Ultra X40 loudspeakers. Okay, thank you very much. Chat is cooling down. It's Friday. I'd say, you know what? Miller time. Stay safe, stay healthy, and see you the next time.